In this problem, we're given two expressions that we need to compare and see if one is equal, smaller, or greater than the other. So in part A, the expressions are the number of ways to choose 5 people out of 10, and we know that number to be 10, choose 5, as compared to the number of ways to choose 6 people out of 10, and we know that to be 10, choose 6, which we know is also equal to 10, choose 4. And by doing the simple calculations, we can see that 10, choose 5 is larger than 10, choose 4. Now, looking at part B, we're asked to compare the number of ways to break 10 people into 2 groups of 5. So 10 people into 2 groups of 5. 2 groups of 5. And we need to compare this to breaking 10 people into a team of 6 and a team of 4. Into a team of 6 and a team of 4. Now, let's start with the right side here. If out of this 10 people we select 4, the 6 that go on the other team are determined. So the number of ways to select this the number of ways to break this 10 people into a team of 6 and a team of 4 is the same as the number of ways of picking 4 people out of 10. And so that is 10, choose 4. Now on the left-hand side, you might say, well, the number of ways to select 5 people out of 10 for the first group is 10, choose 5. And if I select 5 people for the first group, the second group is determined. So the number of ways to break 10 people into 2 groups of 5 should be 10, choose 5. But be careful here, because when the number of players on the 2 teams are equal, this term 10, choose 5 here is actually overcounting by a factor of 2. And here's the reason why. So if we have team 1 here and team 2 here, one of these 10, choose 5 groupings could be A, B, C, D, E, F, G, H, I, J. But another one of these 10, choose 5 groupings is F, G, H, I, J for the first team, and then A, B, C, D, E for the second team. So notice the only difference is if the 5 people A, B, C, D, E go on the first team or go on the second team, but the way we grouped the 10 people is still the same. A, B, C, D, E in one group, F, G, H, I, J on the other group. So it doesn't really matter which team the 5 people belong to. We still grouped the 10 people the same way in both of these scenarios. And so the 10, choose 5 number overcounts the possible groupings of 10 people into 2 groups by a factor of 2. So this value should actually be divided by 2. And when we do this division, we see that the left-hand side is actually now less than the right-hand side. Now looking at part C, we need to compare the probability that 3 people in a group are born on January 1st. So 3 people born on January 1st. And we need to compare this to the scenario where 3 people are born on January 1st, 2nd, and 3rd respectively. So the first person is born on January 1st, the second person on the 2nd, third on the 3rd. So notice that each of the 3 people has 365 choices of days to be born on. So the number of triplets of these birthdays is 365 to the 3rd power. And each triplet is equally likely. So the probability that 3 people are born on exactly January 1st is 1 out of 365 cubed. Similarly, on the right side, again, each of these 3 people has 365 choices of a day to be born. That's 365 cubed possible triplets of birthdays. And we're interested in a specific case where the first person is born on Jan 1st, second on 2nd, and third person on 3rd. So that's again 1 out of 365 cubed, and so the two expressions are equal. Moving on to part D. In part D, we're given this game. So Martin and Gail are playing this game, toss the coin. So Martin will win, and so that Martin and Gail will keep on tossing the coin unless heads appears or tails heads appears. So these two are the stopping criteria. Otherwise, they keep tossing the coin, and Martin wins. Martin wins if and only if heads appears. So we need to compare the probability of Martin winning to 1/2. Now, to compute the probability that Martin wins, let's consider two cases. Case 1, first toss is tails. Well, notice that if first toss is tails, Martin has no way of winning, because let's say the first toss is tails, let's say the second toss is tails, we continue as long as we see tails, but as soon as we see heads, we now have tails heads, which is a stopping criteria. So the tosses stop and Martin has lost. So if the first toss is tails, Martin loses automatically. He has no way to win. Now let's consider the second case. First toss is heads. If the first toss is heads, then we need to see what the second toss is. So if the second toss is also heads, then we get heads, Martin wins. Otherwise, if the second toss is tails, so we have something like this, heads, tails, then we're going to continue tossing as long as we see tails, but as soon as we see heads, we have a stopping criteria, TH. We're going to stop, and Martin has lost. So if the second toss is tails, Martin loses. And so we can devise a sample space consisting of two tosses. So we either have heads, we have heads, tails, we have tails, heads, or tails, tails. And notice that Martin only can win if we have heads, heads. In any of the other scenarios we saw, if the first toss is heads, second toss is tails, or if the first toss is tails in these three scenarios, Martin loses. And since each scenario is equally likely, Martin wins, probability that Martin wins is 1/4, which is definitely smaller than 1/2.